Going over the September paper, starting with question 6. So this first one, log laws, you could use the subtracting log laws where you divide the two logs and the adding log laws where you multiply the two logs. So I've used the division one here for this part here inside the internal brackets, and then multiply that all by 2 here using the multiplying log law here. That should have simplified quite nicely because we need to multiply all of the first part by 2, but you've got this denominator here of 2, so they cancel out nicely. And then you can just raise it all to the base 3 because you've got a base 3 here. So these parts will nicely cancel out, leaving you just this element here inside these brackets, and that's equal to 3 to the power of 2, which is just 9. And then 9 is equal to this, and then we can just balance it like in normal equation here. I've just multiplied both sides by x, and then I can just continue balancing through, which would give you an x value of 4. For question B, you are given again log y is equal to 1/8 is equal to this. So starting once more by thinking about what this implies. So I know in my log laws that this value to the power of this value should give me that value. Is one of my first log laws. Therefore, I can simply just write y to the power of minus 3/2 is equal to 8. Rearrange this. I know I've got negative power here, so I can do 1 over that, get rid of the power. Now these are both over 1, no 1 under 1. Then from that I can say, all right, I can use the reciprocal of both of those and to say that this is just equal to 8. And lastly, I can once more say, all right, y to the power of half is equal to 2. I can just say y, or the square of y is equal to 2. I can just square both sides and I get this. For question 7, you have a vector question, and first part you have to show that this vector OQ is equal to 3/4 A plus 1/4 C. So I started looking at this by outlining AP and looking at what I'm given in this information here, that AP is 1/3 of AB and OQ is 3/4 of OP. So given I know these, I can write them in terms of C. So if AP is 3/4 of AB, then AP also must be 1/3 of C. OP must be then A plus that 1/3. Okay, so nice and easy to do that one. To get from O to Q, then I'm then going to look at my 3/4 of OP, so 3/4 of the way, which is just that, and most of you've got that right as this, and that's your quick proof. If you want to show that a Q lines on this, very easy. If you show that they're parallel and you show that it's a scalar or some multiple of a particular vector, and you also can show that it starts at some point, it's quite easy to show that a particular points on a line. So here, I know that AC is minus A plus C or C minus A, and AQ is AO plus OQ. Therefore, I can add these together and I get this sum here. And if I look at that simplified, when I collect like terms, I can see that this here is the same vectors. They have a factor in common, but actually it's 1/4 of this. Okay, so this actually is a scalar of AC. Okay, so they are indeed going to be parallel because they're factors or multiples of each other, and they're collinear. They both start at A and they go in the same direction. Therefore, Q must be on line AC. Question 8. You've got curves, got this equation, and 2 stationary points, and you want to determine the coordinates of points where these two, a line which goes through these two, will go through the x-axis. So first of all, using differentiation, you can find the coordinates of the given stationary points. Okay, so you can see if you use differentiation, you end up with this, And if you solve that by setting it to 0, because the gradient at those points is going to be 0, you get two x coordinates for which the gradient is 0. And you can find the actual coordinates by putting the original x values into your original function and getting out your two y values. So you now know the full coordinates of the points of those stationary points. And then you can go a bit further by saying, okay, I know the the 2 points. Therefore, given those 2 points, I can work out the gradient between those 2 points by doing the change in y, which is this, and the change in your x values, which is this, which gives you a grade of -8. And then all you need to do is, if you know a particular coordinate, you can plug in either one of these coordinates into y is equal to mx plus c. I've used the bottom one here, and you can see that that gives me a c value of -9. So once I've got the equation of my line here, y is equal to -8 minus 9, I can say, all right, this is going to cross the x-axis where the y value is 0. So I set that to 0. And then I solve for x, and I get a coordinate here for where the line crosses the x-axis. Okay, here you've got a curve, y is equal to ln x. It's stretched by a factor in the x direction. You should know that things that affect the x directions are always going to be inside brackets, so, and they're going to have the opposite effect. So if it's stretching outwards in the x direction, it's actually going to be divided by a factor of 3. So if it was x before, it's going to be x over 3, or 1/3 of that, straightforward. Describe fully a simple transformation from this curve to this curve. So here, you would have used completing the square to have a nice form so you can see exactly what's happening. So here, take my x squared and x terms, reduce them by a factor of x, and we end up with this here. And then we get this additional bit which you subtract, and you end up with this. So that is what this is really equivalent to, and we can compare that to this. Now we can see inside the brackets, we can see what's happened to my x value. So straight away, going from x squared to x minus 3 all squared, that is going to, first of all, going to be a move to the right 3 units. See, I put plus minus. To move to the right 3 units because it's a negative here. And then I've got to go from 1 to -1. Okay, so that's going to be down 2. Okay, there we go. Okay, question 10. We've got this diagram of this curve, and we can see a few things about the curve. We can see a turning point here. We can see one point of intersection here. We know it's a parabola given the order of the function here being 2. So we can tell straight away that there's going to be a line of symmetry here, and we should be able to figure out something about that straight away. So we're asked to show that the function is actually this one given. Now, there's a few ways you can show this. I'm going to show you another one on top of this one actually. So straight away, you can see that this is a midpoint here in your x value. So 3 is your x value. So between 0, so not 0, an x value of 1 and another x coordinate, 3 is the midpoint. So very quickly, you can say x plus 1 divided by 2 is 3. Working backwards, you can see that other x value is 5. So now you've got the 2 roots, okay? So we will introduce a k value because this even could be 1, but we know straight away that those are definitely going to be roots. When you solve it, you're going to get those roots. K is going to be some factor which you might have to multiply by to get the correct corresponding y value, okay? So here, when you do expand this, we get this here inside the brackets, and I can see that's not the same as that. However, I can see it is a factor of the function we're given, all right? For this to become that, we can just multiply everything by 4, okay? Okay, so here's a slightly different approach to it. So we definitely know in completing the square form just by looking at the turning point of 3 minus 16 that we get the equation in this form, okay? And I've also put k outside is going to be some constant that we may need to multiply. It may be 1 and just display. Here, expanding the central part of that expression, we end up with this, and then I can multiply out the k and I end up with this. Now crucially, I can do the whole part, but the only part I really need to focus in on is this last constant part. I know that this is going to be 20, okay? Given the initial expansion is going to be 20. Therefore, I can say 9k minus 16 is equal to 20, so backwards, and I get the value of k. If I substitute k back into this, I should get this expression, so you can use that to check. In part B, you are given the area of this part between that root there and the value a. I suppose we've already figured out that this is 5, 0, and we need to now use integration to work backwards to find that. So I will set my upper limit as a here, my lower limit as 5, and here I will have this expression. I will then integrate these, raising the power by 1, dividing by the new power, and show what my limits are, but also in each case it's going to be equal to 100 over 3. So I have all of these, and I can then put in my limits to my integrated expressions and subtract them to get the area. So when I substitute a and I substitute 5, I get these. Here is still my expression with the a substitutions, but this will simplify quite nicely, quite quickly. Straight away you should see all this is going to just drop down to just 100 over 3. So these last two parts are going to cancel out very, very quickly. As it's divided by 3 and this becomes 0, I can multiply both sides by 3 and you end up with this, and then you can solve very quickly for your values. Now in the diagram you can see, well, this cubic here is going to give you a few solutions, and we can see a is definitely going to be positive and it's definitely going to be inside, and we can see it's going to be non-zero. So immediately you can factor a and you can reject 0 as a solution. Going down to a quadratic, you'll get 2 solutions here. So here, check these in your calculator, but crucially, you get something which is going to be greater than your midpoint, or you could use 5, whichever one, or less than that. If you get a value which is less than 3 or 5, you certainly know it can't be a. In this case, this value has to be rejected because it's going to give you a value that isn't greater than that midpoint or 5 here, so you can reject that, but it's important that you do so. Question 11. Now this one's a little bit more tricky because whilst there is a few answers which you give you correct answers, there is quite a scope of answers which you can give and still get the right answer. As long as you're reasonable, thinking about the context carefully, you will get the right answer. In fact, I'm going to add the mark scheme elements here so you can see exactly what's happening here. So before I do so, okay, I've added these. So the first question says, use this chart to explain which of Birmingham and Liverpool has the larger proportion of people in employment who use their UMLTR in 2011. So looking at your number of users between these two cities, you can see they have roughly the same amount of usage. Now the scale's not, well, you can't see it so as clear as you want it. You can't be precise with yourself. But you see they have roughly the same size. However, you can see that the population of people in employment in Birmingham is larger. Therefore, whilst they have the same amount of UMLRT users, this amount in Liverpool represents a larger proportion. So that one's quite straightforward. Okay. The next part says, one of the researchers said that between 2001 and 2011, the increase in number of people in employment who use their UMLRT is greatest in time and where. Then it says, Sam says, but what matters more is which region has the greatest population, the greatest increase in the proportion of people in employment who use the UMLRT. Looking at the diagram, you can see, yes, this is pretty much going to be the greatest increase. But Sam's saying actually it's the proportion, so comparing it to the populations. And it says, give a reason why the planners responsible for the building of the trains and maintenance of the infrastructure might disagree with Sam. Okay, so the main things you're going to be looking at if you're someone who's responsible for that infrastructure and planning it is the number. So looking at the mark scheme, it's mainly the number that's the most important thing here, okay? You also might want to consider if you go down a route of proportion, being that if it's a small proportion of a large city, it might be still be quite significant. But if it was a very, very, very small city and there was a large increase, that might also represent a very small number at the same time. Question C says, explain whether those responsible for encouraging, that's important here, the greater use of public transport would agree with Sam. So again, looking at the mark scheme for that particular question, you might want to talk about it being a good thing that more people are using the proportion, so using the transportation, and the larger proportions will actually say, okay, more people are using that. And you could argue that it's because out of the whole proportion, it's people moving away from other forms of transport that actually could be detrimental. So it has a environmental good from those who may be using cars, who may be moving over to using the LRT. So there's a host of reasons you could give. But again, some questions here like this, or some parts I'm asking here, it is the size or the number that's the most important thing. The number of people, the volume that's actually going to be using that might cause demand in the system in the first place. But again, you get quite a range of answers that are valid for that one there that you could give. Okay, the last question in this section, it says the charts are compiled from data in the large data set by using those LA local authorities which contain UMLRT stations in each region. Explain a disadvantage of using this data. The main one that I thought of is that there may be users of the system who reside or live outside of the system. Example, people who might commute into that particular local authority from outside, which aren't representative, and they might not use the systems within their local authority. So again, a bit of a range in terms of the answers that you could give. Have a careful look at these because I think quite a few of these were given. All right. Question 12. I think for the most part, this was answered well. You've got a spinner and it has size numbers 1 to 4, and you've got the scores that it could be landed on and the probability of landing on each of the scores. So it's a fairground game, and each player has got 2 spins, and they'll win if the total of the scores is greater than 5. So you will need to look at ways that could happen. So it could be a winning if you get a 6, a 7, or a 8. Then you got Zion, who says, if I play, it's more likely that I win a prize than I won't win a prize. So he's thinking it's quite fortunate, and his odds are good. Okay, so you want to determine whether he's correct. So I've just drawn this table here to show all of the possible scores, and we can see it is these that we're interested in. And whilst there is a wider range of scores which are losses around here in the top upper left hand side, that is not necessarily representative of the total. You can't just say here it's going to be 6 out of 16 as chance of winning. You just need to look carefully at the table and the probabilities. So here we're looking at the probability first of all of obtaining a score of 6, and this could happen by getting a 2 and then a 4, a 3 and a 3, and a reverse of 2 and 4. The first score could be a 4 and then a 2. Then all we need to do, because these are going to be happening together, they are intersecting properties, they're all and. So it's this and this, this and this, and this and this. So we're multiplying those, but it could be each of these instances or outcomes, or the adjacent outcomes. So we will need to add these afterwards. So these are all the probabilities ways of getting a 6, and we can add these up, and we end up with 20 over 72. This same thing could be done when we look at ways of obtaining a score of 7, which could be a 3 first and a 4, or a 4 first and then a 3. And likewise, we do the exact same thing by adding up the ways that this could happen, this or this. And lastly, 8 can only happen one way, and that's if you get 2 4s. So again, it's going to be 1/3 times 1/3 for the probability of that happening. When you add all these together, you get half, which is 50% chance. So not yes. Zion is incorrect because it's not more likely, it's equally likely. All right. Lastly, we've got this one. You've got a school which contains 522 students. In the past, the proportion of students who bought lunch at the school canteen was 1/3. Following a change in the lunches provided in the canteen, governors want to test whether this proportion has increased. That's going to be important later on. They want to test to see whether this proportion has increased. They decide to allow one term for the students to become used to the new system. They note the number of students who buy lunch at the school canteen on the last day of term. They use the number to carry out a hypothesis test. First of all, state a suitable null and alternative hypothesis. So straight away, you should be in with your H0, what that represents, given to you by the proportion in the original statement. And we are looking for this proportion increasing. So your H0 is going to be equal to 1/3. And if there's going to be a change, you're going to know this proportion is going to be greater than 1/3. This statement is very important for this question. You need to show what P represents. So here, where P represents the proportion of students who brought lunch in their canteen. Then it says the number of students who buy lunch at the school canteen on the last day of term is 201. So we are then asked to carry out a test at a 5% significance level to see what this means. Okay, so here I can see my variable x is distributed binomially. And I can say the test is out of the 552 students, where the probability of success is 1/3, and I'm going to be testing against an x value of 201. So I can see for my probability of x being less than 201 being this amount. However, if you've got the fancy calculator, you would have gone straight in and said, okay, P of x being greater than or equal to 201, and that would have given you straight away 0.0688, and you'd have said, okay, this is greater than 0.05, so it's greater than my significance level, therefore it is not in my critical region, therefore I cannot reject HO. I cannot reject HO. There's insufficient evidence at 5% significance level to suggest that the proportion of students who bought lunch at the school canteen has increased. Okay, so important that you are putting in this, important you're putting in these, testing against your significance level, stating that you're rejecting HO or what's happening with HO, whether you're rejecting HO or not. The significance level I always recommend, and again, it's not proof, it's evidence, and whether that evidence is sufficient or not. Lastly, part C suggests one reason why the conclusion of test may not be reliable. The last day of term is typically a day that's not structured like most school days. Various things can happen. There may be events. Some kids may not be in. Quite a few different things might be taking place in that. But the last day of the year in a school is typically not a typical school day.